So welcome back, everyone, to our second lecture on numerical relativity, and in particular, the theory behind numerical relativity. What I will cover with you in the next hour is finishing our derivation or writing down revolution equations of Einstein's equations in what we call the ADM form. I will briefly touch on well-posedness in a physicist's term. So it's not going to be very rigorous, but I hope will give you a bit of an intuition of what the issues are and how we can fix them. And then I will touch upon gauge conditions and initial data. Each of them are really just a taster. So it's going to be quite superficial because each of these topics could be covered in at least 1 or 2 lectures by themselves. And Piotr is asking about the Mathematica notebook. I sent a box link to the organizers. If that hasn't come through yet, if you give me a few moments after my lecture, I will put the link in the chat, in the Zoom chat, so that you can access the notebook. Okay? Do we have any other questions before I get started again? Okay, so I don't see anything. Let me just start sharing my screen. And now going back here. Okay, so what we stopped with before our break was to start decomposing Einstein's equations in vacuum in a space-time form, and by contracting our equations with a normal vector, we could isolate the constraint equations. So that is a set of elliptic type partial differential equations that we would typically solve for the initial data. Now, if we take our Einstein's equations and project them onto the hypersurface in both directions, we actually end up with an evolution equation for the extrinsic curvature. And that's what I'm going to write down next. So to get the evolution equations, as I said, we will project our field equations. In this case, we just have our Einstein tensor, and let me just actually relabel those to have mu and nu as our free indices. So we take rho and sigma here, and then I'm projecting both indices with our projection operator equals to 0, and that will give us an expression for the Lie derivative of the extrinsic curvature Kij along the normal vector. And if I rewrite those the expressions that I get, I will end up with the following. So I have an evolution equation. I will write it now in the form partial, the time derivative of the extrinsic curvature equals, and here we have our Lie derivative along the shift vector of Kij, which contains spatial derivatives of the extrinsic curvature and of the shift. And then we have here minus the second derivative of the lapse function. Remember, I use capital D for the covariant derivative of the 3-dimensional metric plus lapse times the 3-dimensional Ricci tensor. And let me just, for consistency, keep my annotation 3 here, plus the trace of the extrinsic curvature times the extrinsic curvature minus 2 times this particular contraction here, k lower indices ik, k upper index kj, and we're closing the bracket here. And this is our dynamical evolution equation that we get by decomposing Einstein's equations. Let me just write down again our kinematic evolution equation here at the bottom, which was the one that we got just from the definition of the extrinsic curvature, where we have the time derivative of our 3 metric, or induced metric, equals 2, and now I'm writing it in the same form. Time derivative of the 3 metric is the Lie derivative along beta of our 3 metric minus 2 times the lapse times the extrinsic curvature. Yeah, so these are our evolution equations in Einstein's gravity, written down in the form that in numerical relativity we typically call ADM, so Arnold-de-Samisna formulation, even though we know very well that this extrinsic curvature is not exactly the canonical momentum, but it's related to it. Good. So I wanted to add a couple of notes. So I will continue on the next slide. And the first one is why I've actually written down the equations in this form. So I'm now making connection to what we typically implement in a numerical relativity code. So if you look at these equations very sharply, we will have realized that I on purpose wrote something that's time derivative of my quantities on the left-hand side, and then I have my quantities, the variables that I want to evolve, and only spatial derivatives thereof on the right-hand side. And yeah, so just as a side note, the structure of the equations is such that we have the time derivative, and let me just call U our vector of variables. Yeah, and that is related to a function of just the spatial derivatives of our variables. And again, this is our very schematic. So the second spatial derivatives, the first spatial derivatives, and the quantities themselves. And now in practice, we adopt what we call the method of lines, where the right-hand side, that is the function that depends only on the spatial derivatives, and the vector variables themselves, we can use or choose the discretization that we want to use here. So we choose a type of discretization for just the spatial derivatives. Yeah. So, for example, in the Einstein toolkit, we are using typically finite differences, finite difference stencils for the spatial derivatives. If you are interested in, well, the spec code uses a different formulation, but they use spectral methods for the spatial discretization. And of course, we also, so even within the finite difference schemes, you can then choose the order of your finite difference stencil that you want to use. So in the Einstein toolkit, we can vary between fourth order, which is typically just for testing, to sixth or eighth order if you want to have more accurate computations. And then independently of that, so the right-hand side, so all the spatial derivatives and the quantities are computed on the spatial grid, and then we can use a different scheme, a different time integration scheme to evolve that forward in time. Yeah. So on the right-hand side, on the left-hand side, we have our time derivative, and we can choose our favorite time integrator that we want here. It doesn't have to be this finite difference scheme, or it doesn't have to be a spectral method. And one of the typical choices would be, for example, a Runge-Kutta fourth order scheme. Yeah, and that's because we had this question before, why did I make this dependence on time explicit? That's precisely the reason. So if I have my equation, I want to write them in this form, because then I can very easily implement them in my numerical relativity code. And the other note that I wanted to make, we already touched upon in the end of the last lecture, so that's another note, is that we typically adopt a free evolution scheme. Yeah, and that means that we solve the constraints only for the initial data. but we don't solve them throughout the evolution. And in particular, we just monitor the constraints throughout the evolution. To verify that they remain satisfied in our numerical scheme. Yeah. Mm. And what I mean by that, if I say we check that they remain satisfied, they will always be non-zero because we always will have some numerical error here, but typically the typical magnitude of the constraint variation that we find in 3+1 evolutions is of the order of 10 to the minus 5, 10 to the minus 6. So if you get that, then you're absolutely fine. If you get a constraint violation that's larger than that and outside the black hole, then you should get worried and double check and triple check your code. Yeah. And mathematically, why does this work? So you can show, as I mentioned before, that if the constraints are satisfied initially, they remain satisfied throughout the evolution, and you can use Bianchi identities to show this. Yes, I use a Bianchi identity to show that constraints remain satisfied if they're satisfied on your initial slice, and this is what you're posing if you're solving the initial data properly, and if the system evolves according to the Einstein's equations or your evolution equation. Okay, good. So these were a couple of side notes that I wanted to make before actually going a bit deeper into the formulation. So now we are going towards this question of mathematical well-posedness of the equations. And if you had the time, or if you want to play around a little bit, I invite you to implement the equations that we've just written down and try to evolve just flat space-time. So flat space-time in 3+1 dimension. And what you will see very, very quickly is that your constraints and your quantities actually start growing exponentially, and small numerical errors that you may have had in the simulation will grow without bound. Yeah, so the equations that we've just written down will lead to an unstable numerical scheme. And the reason behind that is that their mathematical structure is what we call ill-posed. Then the equations we've written down are not a well-posed initial value formulation of Einstein's equations. So what I will do now is to just give you the mathematical definition for well-posedness, just for completeness. And then I will go over, as I said, in a more physicist's version of what we are actually after and what we need to understand and how we can cure all these issues. So let me start with the definition. And if you have any questions in between, you can just speak up or just interrupt me at any time. Okay, so version 1, and this is the appropriate one, is if we have a system of partial differential equations, and let me just use PDE again as abbreviation, of the following form, where we have a time derivative of a function or a vector of variables with a coefficient matrix like so, plus some lower order terms. and we prescribe some initial data of this form. So this system of PDEs is said to be well posed. Or in a well-posed initial value problem, to be more precise. So I'm talking about hyperbolic systems here. If there exists a unique solution that depends continuously on the initial data. And actually, to be more precise, smooth initial data. Yeah. And in particular, okay, so I'm not sure if anyone takes notes. Let me just take a moment. But the second part that we will find here is that we will actually call a system of these equations well posed if we can put a bound on the value on the norm of the function at a time t during the evolution, and the bound is determined by the initial data. So let me just write down what I said in words on the next slide. So in particular, a system of this form is well posed if we have a constant, let me call this little k, and another constant, let me call that little a, such that for all initial data, we have this bound on the norm of the function at some time during the evolution. And this bound is given by this constant k times the exponential a times t. And here we have the function at t equals 0. So it's bounded by the initial data. Like so. Okay, so this is a mathematical description. And of course, so if you're familiar with the topic, then you can now go ahead and actually make connections between this definition and properties of the coefficient matrix that I've written down in the beginning of this problem. But I want to actually take more the physicist's version thereof. So what is our prime example for a well-posed hyperbolic problem? Well, that's a wave equation, right? So we do love wave equations. They are wonderful. They are causal. We know how to evolve them in time. So now let's go ahead and actually make a bit of a comparison between Einstein's equations and the wave equation. So, and that's, as I said, is a layperson's view on this topic. So let's just equation. And actually, let me do this in 2 steps. So version 1 will be just in full 4 dimensions, and I will have Einstein's equations here on the left, and I will have the scalar wave equation here on the right. And of course, the scalar wave equation we all know and love is just the D'Alembert acting on a scalar field phi. And if I expand this and I just take the leading order terms, which means that I can write this operator in flat space, I have my flat space-time metric at mu nu, and the second the second derivative of the scalar field phi, and this equals to 0. Good, beautiful. Now let's take Einstein's equations, and let me take Einstein's equations in vacuum, because most matter terms, so ordinary matter, everything that you get from an ideal fluid, will be lower order terms, so they will not change the structure of the Einstein field equations. So let me just focus on that. So if I take Einstein's equations in vacuum, I can just write my four-dimensional Ritchie tensor equals to 0. And now let's expand that, right? So what do I get here? Well, the first term that I will get is of this form. And again, I will take the leading order terms and derivatives of the metric. So here we have now our flat spacetime metric, eta, kappa lambda. We will find this beautiful second derivative, which is really just the wave operator acting on our metric g mu nu. Wonderful. But if we do the expansion carefully, then you will remember that we also have other terms that involve second derivatives of the metric. Not going to write all of them out, but they will be of this form, plus, and you will have two more terms of the structure. And then we have lower order terms that I will neglect. Yeah, so I'm only interested in the highest derivatives because that tells me about the structure of the equation. Now, this up here, let me just highlight this in green. So this is a wave operator acting on the metric that we want. So this is great. Yeah, this is the equation we want. But we also have these other terms here that we do not want, because these are the terms that potentially or that actually do spoil the well-posedness of Einstein's equations. So if we now go back to the 60s, Madame Chokri-Bruhat has a wonderful proof showing well-posedness of Einstein's equations. And what do we take here, or what we take here is a harmonic gauge. Yeah. So essentially a wave equation for our coordinates equals to 0. And if you do that, then so if you insert that here, then all of these nasty terms that spoil our well-posedness can be made to vanish. Of course, you have to do the calculation very carefully, but that's the gist of it. And we end up with a set of wave equations for our metric. So the cure here is to use the right choice of coordinates, the right gauge to make our equations well-posed. Great. So in terms of history, and I like to point this out because it's, I think it's sometimes a bit overlooked. So in terms of history, I think the community for a long time thought, oh, we have this proof of well-posedness for Einstein's equations, so let's just take whatever formulation we have, and most people had this ADM formulation, and put it in our computers. And once you try to go to 3+1 dimensions, that failed, right? So the reason why a lot of the early simulations in 3+1 dimensions did not go through was the formulations of the equations. So what Franz Pretorius did in 2005, when he had this first simulation of a couple of orbits and merger of two black holes, was precisely to use a formulation very similar to what I've written down here. So he took Einstein's equation, he generalized this harmonic gauge and added some constraint damping. But this is essentially what he used in his first formulation. Now, the second group of successful simulations used a version of the ADM equations, but with a cure to the well-posedness. So let's look at how that looks like as well. So let me go down, first change to black again, and then let's look at a second version for the wave equation. And now I will write this down in 3+1 form, so in the form that we derived before. Okay, so let's focus first on the scalar wave equation. How does this look? So if we have our wave equation here, we also perform a 3+1 split. So we will introduce a quantity, let me, equals minus time derivative of phi, just as very analogous to what we did later on with extrinsic curvature. Now, if we rewrite this, we find that an evolution system that looks like time derivative of phi equals minus pi, obviously, because that's just rewriting this equation. But then if we adopt that also in the wave equation, we find that the time derivative of pi is nothing but minus the Laplacian of phi. Yeah, so just write this out to recognize the structure later on. Yeah, so this is a wave equation written in 3+1 form. Now let's see, let's compare what we have for our ADM equations or ADM York equations that we've written down earlier. So, and again, I will only take the leading derivative terms to analyze the structure of the equations, right? So I don't care about the lower order terms now. So if we take 3 plus 1 Einstein's equations, we had the time derivative of the 3 metric related to minus Kij. And yes, there are terms of the labs that I'm just ignoring right now. But this is a leading order form. So this looks analogous to our time evolution equation for the scalar field. So good. But now if you look at the second equation, so the evolution equation for the extrinsic curvature, what we have here is the second derivative of the labs plus the labs times the 3 Ricci tensor plus some lower order terms that I don't care about. So let me write out the Ricci tensor, right? So what we get here is it's just our second derivative for the labs, and then we have these terms alpha times well, 3 metric gamma LM dl dm of our metric gamma ij. So this one's good, but we will also find these other mixed terms of this form, say, like so. And we, of course, have also the other combinations thereof, and then these lower order terms. So if you ever wondered where this ill-posedness of the ADM equations came from, it's precisely these terms down here that are not like a Laplacian operator, right? So the first term in my expansion, and let me highlight this in green and circle it in. So this is the type of terms that we want. So this is exactly what we have here for the wave equations. But the second type of terms that I highlight here in orange, so these are heuristically the cause for the ill-posedness. Yeah, so what we need to do now, and by now we understand very well how to do this, is essentially find a way to get rid of these terms here. And one of the more common formulations is a formulation by Thomas Baumgartner, Stu Shapiro, Masaru Shibata, and Nakamura. So short BSSN. Let me just write down the variables that you introduced for those and the leading order terms. I'm not going to write down the system in detail because then we can fill the entire slide, and that's not very instructive, I think. But let's just have a quick look at the leading order terms. And we also now have a second formulation that usually goes by Z4 in different variants thereof that also has a constrained damping term here. I'm not going to write this down, but this is actually an even better type of formulation because it helps us keeping the constraint violation down. Good. So yeah, I do have some space here, and I will try to use only this space to write down the BSSN equation, BSSN variables. As I said, not very instructive to have them in great detail. Let's get the right one here. So let me just pure in quotation marks. So Baumgartner, Shapiro, so they were in 1999. Shibata and Nakamura were actually earlier than that. Yeah, so this is a BSSN formulation. Or we have something like that form. So the variables that we have in the BSSN formulation are a conformal factor. Let me call this W, which is a metric of our, determinant of our 3 metric to a certain power. We have the conformal metric gamma ij tilde, which is this conformal factor squared times gamma ij. So this conformal metric is not actually a tensor, it's a tensor density, and it's chosen in such a way, typically, and now there are extensions thereof, that the determinant of this conformal metric equals to 1. Then we also decompose our extrinsic curvature into a trace and a trace-free part. And the trace-free part, let me call this Aij, is also has also conformal decomposition attached to it. So here we have Aij minus 1/3 gamma ij traces, the trace-free part. And then we have a function that's called the conformal connection function, gamma tilde I, which is a contraction of the Christoffel symbol for the conformal metric, and with the determinant of the conformal metric being 1, this can actually also be written as a divergence of our 3 metric here. Good. So these are the quantities that we have. So we introduce those quantities, and then we also add the constraints so essentially adding a 0 to our equations in a smart way, such that the evolution equations that we end up with are indeed well posed. That is, if you look at the structure, then to leading order, the highest derivative terms can always recombine to give you a wave equation. Okay, so this is all I'm going to talk about. The formulation. If you want to know any of the details, you're very welcome to look at the textbooks that I mentioned earlier, and typically, or any lecture notes will have the full set of equations as well. But as I said, they're a bit lengthy to write them down here, and I would like to talk about a couple of other topics before we conclude the lecture today. In particular, the next question that I want to ask is how do we actually choose our gauge, meaning our lapse and shift, such that we have a stable evolution, for example, for black hole spacetimes. Now, generic question, let me just continue on the next slide to do so. Yeah, so the next question is the choices of the gauge. That is, how do we pick the lapse and the shift? Now, the easiest choice, you could, of course, I argue, since we have the freedom to choose what lapse and shift are, we have this gauge freedom, why don't we just pick lapse being 1 and shift being 0? And yes, you can do this, and it would make your equations look much, much simpler. But that also means that any geodesics that you have will automatically focus on your singularity. So you will automatically reach the black hole singularity in a finite evolution time. So while that may be useful if you just want to test your code and you can work with that, it's not very useful if you actually want to have a stable simulation of a single or a binary black hole, right? Because if you know that your code will crash inevitably with this choice, then that's not the best you can do. So instead, I have a little bit of a wish list of what I want these gauges to do for me in a numerical simulation. So again, just as a warning, yes, so the simplest choice is not always the best. And in particular, if you take what we call geodesic slicing, so we have the lapse being 1 and the shift being 0, we reach a black hole singularity in a finite time. Good. So what do I want instead? Well, as you can guess, especially with this example given, I want to avoid reaching the singularity, right? And of course, there are 2 ways of what you could do. we want to avoid the singularity. And by that, I mean the physical singularity. Now, one thing that you could do is, in your numerical domain, excise the region inside the black hole, so the region that contains the physical singularity. And at least in classical GR, because nothing can travel from the black hole interior to the outside, it really shouldn't matter what you put in that interior region, right? So that's the standard law, so you can excise this inner region. And it's very doable. That's essentially what spec collaboration uses. I believe that's also what Franz uses, or has been using at least in the past. However, if you want to evolve a binary, it becomes quite cumbersome to follow this excision, so to follow the motion of the black holes and always have the excision at the right place with the right boundary conditions. And in particular, if you want to reach high black hole spins very close to extremality or high mass ratios, then you have to work a lot to get this excision region right and to put the boundary conditions right. So many of the other numerical relativity codes use something different, where we basically have a smart choice for the lapse and shift, and that's the one that I will tell you about in a moment. But just for completeness, so what I'm going to tell you here today is really just a taster. It's not the only thing yet you can do. It's just the one that we tend to use in the Einstein toolkit, and a lot of the large group part of the numerical relativity community is using. Yeah, so wish list, I want to avoid the singularity one way or another. The other wish that I would have is that my evolution equations, together with the gauge conditions, form a well-posed system of partial differential equations. Yeah, and again, this property, this well-posedness, is a necessary condition for numerical stability. So I better have that in my formulation. And then the last one is that I also want this to be easy and straightforward to implement. So in particular, I want to avoid elliptic choices, not because elliptic equations are bad, but they are very expensive to solve numerically. So I would prefer to have evolution equations for my lapse and my shift. And so specifically, I would avoid elliptic equations. They're computationally expensive. And instead, I want to use evolution equations. Good. So one of the most common choices is what we call the puncture gauge, or even moving puncture gauge. And this has two parts. So it's a condition for the lapse, which is called 1 plus log slicing. And the condition for the shift is called gamma driver condition. And we will see in a moment why that is. Good. Yeah, so let me just give you the equations here. So in particular, for this 1 plus log slicing, what we have is the following form. So we have an evolution equation for the lapse here that goes like -2 alpha times the extrinsic curvature, potentially minus some trace of the extrinsic curvature minus some background curvature. For example, one of the early works that I did as a PhD student, we did simulations in asymptotically de Sitter spacetime. So we've actually found it useful to add this additional background curvature to our evolutions. but this is what we typically use to evolve the labs. Now, let me just highlight a couple of properties of this labs. So it collapses to zero close to the singularity. So with this choice, the lapse goes to zero near the singularity. Which is good. We also find that the spatial hypersurfaces cannot be arbitrarily close to our physical singularity. So, and that is a singularity avoidance, right? So we will reach a certain part of the black hole interior, but we will not reach the actual singularity. And that helps us with the numerical simulations, because if we don't have the singularity on the grid, we're basically good. So we have this singularity avoidance property. Yeah, that is a spatial hypersurfaces cannot be arbitrarily close to the singularity. So if I were to plot our slices in a Penrose diagram, let me just try this. I'm not very artistic, so I apologize in advance, but I hope I can give you a bit of an idea. So if I take our Penrose diagram here, our singularity up there, then our slices would typically look something like this. Go here, oops, and they're smooth, so go here into the interior and end up over here. So if we evolve that forward in time, again, they go in and then basically pile up close to this surface here, and that surface is at a radius of 3/2 over mass, and mass is a black hole, the mass of the black hole here. So this is what our slices do, and as I said, my drawing is not great, but I really just wanted to give you a gist of what's happening here. And that's what we are doing for the labs. Now, for the shift, we also derive a time evolution equation. And here, what we have, and again, there are actually different variants. So let me just give you one of the variants here. We would have the time derivative of our shift vector, and that is given by, so this is just a coefficient here, times the conformal connection function, minus, and this is another constant eta, which is dimension 4, and the shift itself. So this part here is just an advection term, whereas this first part here, if you remember, this conformal connection function was defined as, or could be shown to be related to the derivative of our conformal metric. So what does this do in practice? If we have a numerical evolution and we have a binary system, and you can see my hands, as the binaries evolve through the numerical grid, they would tend to drag the grid along and deform it. So you can develop really large shears in your coordinates. And what this shift condition does is essentially counteract this shear, because if you have too large gradients in your coordinates, again, your numerical code may fail. So what the shift condition does is counteract this shear and these large gradients in the coordinates, and helps to stabilize the evolutions. Yeah, so that's why this particular shift condition has proven very useful. And actually, these conditions and variants thereof were actually known before the breakthrough. So there's a very nice paper from 2002 by Miguel Alcubierre and collaborators, where they have a collection of different choices, both for the gauge choices, both for the lapse and for the shift, both elliptic and hyperbolic choices. So if you're interested, you may want to look at this paper, or he also has a very nice summary, of course, in his textbook. Okay, so that's all about the gauge. And the last part, in the last 10 minutes that I have, not take all of the 10 minutes, let me at least get 5 minutes to talk a little bit about initial data. And again, given the shortness of time, I will be very superficial, just give you the main ideas here. And then I hope that would give you at least a starting point if you wanted to delve deeper into the topic. So let me just go down, actually start on the next slide. So this is the last part for today, is really a brief summary on initial data. And again, I will only present part of one version of what you can do. This is not unique. There are other ways to construct initial data as well. But this is, I think, the most instructive one. So the goal that we have here is to prescribe the three metric gamma ij and the extrinsic curvature kij on our initial time slice. I'm not talking about the lapse and shift here at all, because there are gauge choices, and so people tend to just pick a choice and then have the lapse and shift adapt through the evolution equations that I've written down on the previous slide. Good. So let's do some counting to isolate different parts of the problem if you want to solve for initial data. So if we count the independent components, right? So the three metric and the extrinsic curvature are both symmetric. Then three spatial dimensions if we're in adapted coordinates. So what we need to do is specify 12 components of these two tensors. Yeah, 12 independent components, I should say. Good. Well, I made this point about using the constraints to solve for the initial data, but the constraints are just four elliptic equations. So they will specify four of our independent components, but not all of them. So how do we specify the remaining 8 components? Well, that's up to us, and is essentially motivated both by the physical setup that we want to study and possibly a technical simplification. Yeah. So for the remaining 8 components, and here we will have motivation by this physical system. And something that will help us to simplify the equations. Okay, good. So there are two things that we can do. And what's commonly used, at least in the Einstein toolkit, I believe also in Giacomo, and I will mention those in a minute again, is a conformal decomposition Nerowitz, and I hope I pronounced the name correctly, where we do the following. We say, okay, let's take our metric, gamma ij, and now decompose it into a conformal factor. Notice that this may be a different conformal factor than we had before in our BSSN formulation, to a power of 4, and let me, to make that very clear, put a head on the conformal metric here, because it's not the same, necessarily the same conformal metric as we had in the BSSN formulation. And we decompose our extrinsic curvature as follows. So here we have conformal factor to the -2, and again a trace-free part of the extrinsic curvature plus 1/3 psi, the conformal factor to the fourth, gamma ij hat times the trace of the extrinsic curvature. And the choice of the conformal factor here is such that the divergence of the extrinsic curvature translates in only the divergence of the trace-free part of the extrinsic curvature. Right. So there's a simplification here by choosing the powers of the conformal factor. Now let's have one look for one example. Let's just look at a single non-rotating black hole and see how we would get the initial data for that. I don't believe we really have the time to talk about the binary initial data, but let's go talk about the single black holes. So just an example. Yeah. In this case, I will, so since it's non-rotating, we have time symmetry. So this gives us already a lot of simplification. Yeah, time symmetry means that our extrinsic curvature equals to 0. That also implies that our momentum constraint is trivially satisfied. So that's good. So we only have to worry about the Hamiltonian constraint. Then we will assume conformal flatness. That is, our conformal metric, gamma ij hat, will just be the flat metric. And if we do that, our the Laplacian operator that we get in the Hamiltonian constraint, if we expand the Ricci tensor, will just be the flat space Hamiltonian. And we also assume, so we are interested in asymptotically flat solutions. So we also assume asymptotic flatness. Yeah, and this is where some of our physical conditions come in. Yeah, so that is, we have that our conformal factor goes to 1 as we reach spatial infinity. And if we put all of that in, we basically get that our Hamiltonian constraint becomes the flat space Laplacian acting on our conformal factor together with this boundary condition. Now, this looks like an equation that we know how to solve. So let's just write down the simplest non-trivial solution that we can find. So yeah, simplest non-trivial solution to this equation is the conformal factor equals to 1 plus some constant, little k, divided by the radius. And now if we identify this constant to be the mass of our black hole over 2, then, well, obviously our conformal factor is 1 plus m over 2r. And now let's actually look at the metric. If we put everything back together, we use our conformal factor that I just derived. I look at, so I insert that our conformal metric is a flat metric, and let's put everything in our line element. So what we find here is our line element is minus labs squared dt squared plus, and the spatial part is what we had just derived, which is 1 plus m over 2r to the power of 4 times the flat metric. So remember, that was our ansatz for the 3 metric dxi dxj. And now if you look at this very sharply, you will actually recognize that this is a Schwarzschild solution in isotropic coordinates. And this is one of the initial conditions, or this is the initial condition that we would often implement if we want to evolve a single Schwarzschild black hole. Well, we do that if we want to benchmark our codes, but it also gives us a primer to extend to binaries. For example, we can superpose the solution to just get initial data for head-on collisions. And let me just add that as a note, as we are at the end of our slides. Yeah. So we superpose the solution for just head-on collision where we have zero momenta. And this is also a seed solution, so we have to work a bit harder. But if you want to look at binaries with linear momentum, so if you want them to be on circular orbits, or if you also want to add spin of to the black holes, we can use this solution as a seed together with an analytic prescription for the extrinsic curvature that was derived by Bowen and York first to get initial data for black hole binaries. And this is just one version of initial data. So together is Bowen and York extrinsic curvature for the momentum. Okay, good. And I think we are at the hour, and even though we started a little bit late, I think I would like to stop here for the lecture part. There were a couple of comments that I wanted to make, but not necessarily write down. So in particular, if you're interested in using a numerical relativity code, there are a few public numerical relativity codes out there. I personally am one of the co-PIs of the Einstein Toolkit, and you're always very welcome to join our calls on Thursdays, 9 a.m. Central US time. We also have summer schools once per year, and actually the last one that we held here at the University of Illinois was recorded. So if you come to our website or to our YouTube channel, you find recordings of the lectures and tutorials if you want to get started with one of the public with the Einstein Toolkit. Another public numerical relativity code is Giacomo, which is relatively new. So that has been developed by Katie Clough, who just got a lecture position at Queen Mary University in London, and also developed by Eugene Lim and Paul Figueras, also both in London. The SPEC collaboration is actually working on an open source code that is called Spectre, and there is development going on. I'm not sure what the status is of the code actually being public, but this is coming out. So there's a lot of infrastructure, public infrastructure out there if you do want to get your hands dirty to do so. Yeah, I did mention the school, and also, so there was a question in the chat I see about posting the lecture. So I will send my PDF files to Brenda and Christian, who have been great in setting everything up. And, I will send my consent that the recording can be public after the lecture. So thank you.
Great, thank you so much.